Okay, shall we start? Sure. Okay, yeah, so let me get started with this part of the module. It's just 2 lectures, quite short, on this, what I'm calling theory of measurements. And this is something with Sourav we were planning actually, the way the school, it's a very short school, 2 days. And the way the school was divided in 2 parts, we basically decided to do a small experiment of actually having an experimental day, like, you know, like in the sense that it's about time. How many experimentalists are there? Like how many? Great, yeah. So, so that was the whole point, that we started realizing that, you know, like students go to schools all over India, and here schools are always like very hardcore theory, not necessarily important for if I'm an experimentalist, the measurements we are doing in the lab and so on. So why not actually have schools where really we talk about everyday problems of experiments, electronics, feedback, data processing. So this I'll be talking mostly about what we do with data collected in the lab. And this is really a trial, so hopefully we'll get some feedback from you after today, that how this today runs, and if it works out, we might actually do a full school, 2-week school on just experimental techniques and so on. So a quick announcement, we basically want, we want to see your posters and the work you have done all through the school. So we forgot to announce, but it will be great if, even if before lunch, all of you can rush, get your posters and put them up, so that all 3 days, all during the entire time, we can actually, during the tea breaks and lunch and so on, we can discuss the posters here. That ICTS will be able to say. Okay. Yeah, so just talk to the yeah, so let me get started. This is a topic, you know, like we are also learning, and it's basically mostly statistics, but then as physicists, we only get to learn things when actually the bridge comes and we need to cross that bridge. So over the last 2-3 years in our lab, due to some measurements and certain issues, we actually realized that we need to relearn all these things of like how to measure, what do we measure, what do we do with the data that we get, and what is a good way of inferring something from what we measure. So that is why let me start with a very, very general question that, you know, why do we measure at all? Anything? Anyone? Like, why do we measure? Very, very general question. There might be 10 different answers, so you can start with your own ones. The class is quite, it's fine. It will be really nice if you ask questions in the middle or take part in it. So, so we measure, there are many different things people can say depending on their taste of how they look at it. Particularly theorists might answer in very interesting ways. But one is to actually gain information. You know, so gain information about, you know, this gaining information is again a very general statement. I'll try to quantify this throughout these 2 lectures, but this might be gaining information about a system in the form of a certain parameter that we want to know. So a parameter that is predicted from a model. Model relies on a parameter, and we want to collect some data and find an estimate for the parameter. But we might also, you know, do measurements for very general purpose of testing, you know, theories, hypothesis, or conjectures and so on. So it might be just kind of, we are really not after measurement of a particular parameter and how well we can measure the parameter, but just maybe like, is gravity quantum, if you want to do some measurements to test that. So it might be like just yes, no kind of questions. And there's another third part. That is why I was asking, but since the class is quite, there's a third very important part we experimentalists use, but usually will not talk about it. And if you talk to a civilian, will say, oh, such a bizarre statement. But it's actually sometimes in very sophisticated manner, we actually use measurements to prepare a particular state of a system, and that's another very growing usage of measurements, and I'll try to come to that towards the very end of second lecture. So these are kind of like whatever you say about the nature of measurements, you can broadly kind of classify roughly in these three directions. And let me just try to, this is something I'll try to do all through the lecture. I'll try to give examples, because it's a very short set of lectures, to kind of quantify what I'm saying so that everyone can take part. So let me just, particularly these 2 points, let me just try to quantify this a little more by kind of an experiment where, suppose you're doing some astrophysical experiments. So you're looking at the sky and you have your, this is your telescope plane. And you're looking at the stars, which are kind of like through optics, like this rather point sources are falling on your plane with some diffraction. They have broadened out. And you know that there is a very bright star somewhere, maybe Sagittarius A star or something like that. And next to it, some people are saying that there is another little star. It's not clear whether there is a new discovery to be found. So how would you proceed to find whether actually there is a star? You would actually look at this telescope. If you, for example, have a counter, a photon counter, usually what these telescopes have. So you will try to create histograms. So these pixels are divided into parts, and you have this like, different ones are actually putting in counts, So these are like counts corresponding to this big star. And then you have these other histograms, which are like varying patterns. You have collected data for a while. So the question is, this is what you have for the data. And you are trying to answer questions. And when you have this kind of data, the question you're asking actually becomes very important. So this is what I was trying to start with, that basically there are 2 kinds of questions you can ask. Like the first question you can ask is that, is there a new star? Right, so this is what I was saying, that this is a yes or no question. And if you see, this is a question of inference or a judgment, that you might say that, okay, I know this is the big star, and these things are randomly oscillating. Is this a new star or not? You need to really answer yes or no. So you can actually draw a decision line, some cutoff line. And you say that anything that's above this is a new discovery, and below that are just noise, right? So this falls above that, and you say that, okay, yes, there's a star, right? And how you choose this line is a completely altogether different issue, and there might be many other things going on, a lot of experience and so on. So, but nevertheless, you are actually this kind of nature of questions where you are actually trying to see whether a theory is right, whether things like, or a conjecture is correct. So this is actually falls under this very broad field in statistics, which is called this theory of inference. These are all like the subfields of theory of measurements. And there's another question. Once that you have you are certain that there is a real star, you're not tuning to the local radio station, there's a real signal. After that, you might actually be interested in more technically, you would like to know the thing of the property of the star. So what is its inherent intensity? So basically, you would like to now know pretty well that where I can actually draw this line. So so you actually might be interested in knowing the new star that you have discovered as a function of temperature and mass. And from there, you might like to infer what was the inherent intensity of the star. And once you're after this, you see that you are actually asking a question which is really relating to a number. Right, you actually want to have a number, and there actually immediately the question comes. This we routinely do is that how well this intensity that I'm quoting, how well this part, how well I can actually specify the quoting, and this part I'll just differentiate by saying that this is actually another subpart of this theory of measurement, which is this theory of estimation or parameter estimation, and we'll hopefully be able to motivate that. This set of lectures will primarily be focusing on this very quantitative statements of how well we can estimate a parameter. That's what I'm getting at, and how well I can estimate a parameter from data by choosing data. But hopefully, I'll be able to motivate that in many scenarios, particularly in certain versions of statistics, these two questions become very similar, actually. Like presently, they look awfully different. Like one is a yes/no question, the other is a number. But many a times, actually, you are inferring parameters of a theory, and that way you are actually inferring about a theory by measuring the parameters and tightly constraining the theory. So any questions up to this point? Very general, say, or comments, or there are experts in the field, if you want to state anything. So these are the key questions. I'll keep stating the important questions. So so that like at least if nothing gets communicated, at least we have the questions in mind. So let me make it a little bit more specific now. So and by the way, like the moment you see this, many of you students might think that yeah.
Actually, have a curiosity question.
Mm-hmm.
When you say about the line of
choice or the decision here.
And then how is the statistical weight of the data plays a role? For example, what you have given might be that for certain statistics.
Yeah. So there are like bits and so on. So that is where, again, like the moment you're talking of the statistics, you see that there is an overlap between the estimation questions, because you're saying that, okay, like, so this histogram is above this line, but how much above, like, again, like you're asking finer questions. And that's kind of exactly what I was hinting. But hopefully if I can come to inference towards the end of next class, some of these examples will become clearer, but effectively, yeah, the questions become similar. So if I now, make it a little bit more vague, that, let me just put this structure that normally we have in mind, a very, very general measurement structure. And this structure will basically be developing everything kind of based on this two block diagrams. So basically, this, I think all of you might be able to map, since there are so many experimentalists, to your system, that whatever you say, it's difficult to argue that basically all measurements are of this kind of a flow, simple flow, where you have a system, you actually have a measurement measurement device, which actually spits out some data. So there are these 3 stages. And based on these 3 stages now, you see that the questions were very general. Now I'm making it more specific because this is what we all know is behind the system. So like behind the measurement. So I can then actually ask again, like now it's a little bit more technical. So I can ask actually now again, like different questions. For example, of course, I'm trying to measure. So I'll be looking at optimizing my measurement. And for now, let's say that we are actually measuring of a parameter theta and a variance or standard deviation or root mean square error of delta theta. This delta theta I'll be specifying more and more. This delta theta itself, there are choices, but basically I'm trying to measure a parameter theta. So somehow I need to do something with the data to come to this parameter theta. And I also need to put the what we call the error bars or an estimate of how much error I have performed. And here you see that the moment this structure is there, and this is what I'm given with this parameter estimation, I can ask now some more specific questions. I can ask, for example, what is the most optimal system state I can prepare. I have not yet defined what I mean by system state, but assume and presume, like since all of you are physics students, that this system is characterized by some state. If it's classical, it's probability distributions. If it's quantum, they're like density matrix and so on. But what is the most optimal state I can prepare so that I actually do very good in parameter estimation? And what do I mean by that? I estimate this parameter with the least amount of error. And similarly, you see that the pattern is very clear. So I can also ask what is the most optimal measurement I can do. Right. So these are both optimality questions. I am designing my experiment. I'm starting to measure some very specific parameter for my PhD, and I would like to design. And these are the first 2 questions, like what is the state the system should be so that I do best, along with what is the measurement. And then there's a third question, which is that given A and B, I did my best possible thing that I could do. How well I can do in minimizing delta theta. Right. So basically, you see that the first 2 questions, as experimentalists, are purely system design question. That what is the state I can prepare? What is the most optimal measurement I can do? I'm still not coming to a point that given the data, what do I do with the data, in fact, to get theta and delta theta? Remember that question is there. That is what will work out. But these are state preparation and measurements, optimal measurements. But given I have done very well in A and B, is there a bound of how small I can make delta theta? Is there a limitation of, is there something fundamental, or I can actually make that delta theta infinitely, like basically 0? And this is the nature of the question. Yeah.
That is taken care of in the third question, right?
Yeah, so basically that's why I have put this optimal in quotes, that you can ask like every English word you should question. So just like I have not defined the state, I have not defined the optimal. And you are very beautifully pointing it out that this optimality is basically the condition C, right? Like what I mean by optimal for state and measurement is actually said by this, that if there exists some fundamental limit on delta theta, I cannot do better than that, then basically, like whether I'm choosing optimally to actually saturate that kind of a limit, like, like whether I can reach that limit. So given that, so let me again, like what we communicate during the class, I don't know, it's very short 2 classes. So let me at least state the important results that I'll try to derive, at least some part of it. So what is known in the community, what are the very important results, and why this field is suddenly very important. So one of the things is that, people are very concerned about, so let me first state the results that we'll try to first appreciate and then try to see how they come about. So the important results are the following. So people are just not interested in just a single system and measurement and data, but actually a series of repetitions of that. This we all know. We have done undergraduate labs that the lab instructor will keep saying that you have taken too less number of data, you will be penalized and so on. So actually, the picture that is there is that there is a series of these measurements, M2 and D2, and so on. And there are many interesting questions. These are the repetitions that we do always in the lab. There are very important, interesting questions in the lab practically. We do not have infinite time to take this n to infinity. We cannot repeat infinite time. There's a finite amount of lab hours. So basically, for example, I can ask that if I repeat this measurement and get all these different sets of data, do I really do better at all? Like if I repeat it n times, do I really do better? And some of the results, let me just state here. So there's a classical result which will work out, which basically says that if you do this and n times you repeat it, so there are n of them. You actually, and you are estimating this parameter. So there's a limit to this parameter, and that you estimate the error in this parameter. And by error, now let me just specify this. I mean root mean square error. I'll specify every point whenever I'm talking of that. So this error actually, basically, so let me put this here, RMSE. So this error, actually, the classical result tells you that this scales as, or this error is kind of delta theta divided by square root of n, which is very interesting, actually. In fact, the classical results tells you more. It's firstly saying that if you repeat n times, and if you calculate for each of them the mean, the variation in the mean, I'll come and stress on this even more later because it's like widely misunderstood, particularly by students often. But basically, the variation in the mean goes down by 1 over square root of n. And another very interesting thing of the classical result is the following, that you might say that, oh, this looks so stupid that, you're repeating boringly n times the same thing. If I, for example, correlate this thing somehow, like use, the first measurements result into the second, this, that, or actually make this things correlated classically, do I do better? In fact, it turns out that you do not do better. It's kind of a very striking result that for uncorrelated measurements, actually, you kind of saturate this bound. So this is one result we'll try to understand. And then there's a quantum version of the result, which sets kind of the this bound. It actually says that, in fact, if you correlate these systems in a quantum mechanical way, you indeed do really well. In fact, this delta theta that you calculate goes in this case as by n. Like this is the best you can do. And by the way, this delta theta measurement is actually the error that you're getting for each individual measurements, right? So And this is actually, if you see, is a main driving force for people who really want to measure well and understand how much information you can extract. Because suddenly you see that if you, for example, are doing kind of this counting statistics, photon counting from stars or from atoms and so on, and you see that you take like 10,000 data points or 10,000 repetitions of the measurement, you see that in this case, basically, you know, like this quantum bound actually gives you a factor of 100, you know, better in delta theta. So you basically, by repeating the same amount, you are doing 100 times better. You are like gaining 2 orders of like after the decimal by actually measuring this. And so hence there's a lot of interest in understanding, you know, what these results exactly mean in the sense that, you know, when you're saying delta, like correlation, is it, what kind of correlation do I mean? And of course, I stated already the classical result that classical correlations doesn't really help. So these are like some inherently quantum correlations you learn in the school of like entanglement being the name of such correlations. But there are also other very interesting results. We'll actually not go too much into this quantum results, but there are also very interesting results that it turns out that actually correlating similar way the measurements or detection actually doesn't really help in the quantum case. Again, like the source correlation is what becomes important. Yeah. Mm-hmm. Yeah, both are experiments, exactly. And this is a very nice question. So, and you see that as an experimentalist, both are actually just giving you a set of numbers, right? But then the question is, how do you, so this set of numbers, and then you have some theory, right? Like that is where the classical or quantum comes in, because you have a system and you have a description of the system. So there is a theory behind it, and that theory is telling you how to, the theory will, or rather the model of your system will have observable, like, you know, variables and so on. So the quantum and the classical only comes in how you are calculating those averages, right? Like, so these are all like stochastic systems, and really in the averages are where the differences are. So let me, quantum statistical, these are all quantum. In fact, I'll state this result in, like, once we do Fisher information and so on, I'll just state this result, I'll not prove it, but then the statistics becomes clearer. In fact, this is just like tilde, actually the real result should also have a square root of m or something. This one? So this is, yeah, so this is basically the, this is the kind of your actually measurement error coming from one, like inherently that is there in the system, right? Like, so for example, no, so for example, like your, this entire thing, you might have a very simple model of your system, which is that you're saying that your system actually is giving you variables from a Gaussian distribution or from a binomial distribution, right?
Or can I think that I have 10,000 data sets, let's say part them into bunch of 100. And I take a average standard deviation of the 100. And that gives me some delta. Then I think that I think that that is the delta.
So this delta theta is the is what is there inherently in your model, or you know, this might be like, by model I mean it might be, for example, you are saying that you are sampling all your data from some Gaussian, you know, some sort of a Gaussian. So then this delta theta is just sigma, but also this delta theta can be just your minimum measurement precision. Right? And then after that, what you're saying, in fact, I'll come to that point, but exactly that is the thing, that you see that this delta theta, it's also important to realize that it is the variance of the mean, or the root mean square of the mean. So for example, one measurement with a series of data, you know, there might be m sets of data, just gives you one mean. right? And then you have 10,000 and you split it up into hundreds. And this is the variance of between those means. Yeah, exactly. Yeah, any other question?
I also have a similar question. So this, when I say F1, M1, D1, so that's
by D1 I mean the data sets. Yeah,
that's one measurement. Or
this is the one measurement, but your data set, you know, like are basically like X1, X2, some XM.
that's okay, but
Right.
you know, there is a characteristic difference.
Or I should put it here in.
See, when you say F1, S2, S3, S4 up to Fn, so that's a different type of measurement. That's a repetition of the same series.
Yeah.
Whereas the first one or second one, they are a data set.
These are data sets. No, can you repeat that question again?
My question is, each one, S1, M1, D1, so that's one data set.
One data set.
Right,
yeah.
Right. And then you repeat this.
Yeah.
The
Yeah.
S2, M2, D2,
Yeah.
and so on. So now from that one data set, I actually have a similar question what Sourav had. So how did you calculate that delta theta? I understand your argument that this might be the minimum error of your measurement detector itself. That part I understand. But apart from that, there may be also a error which might be much more than the minimum error, right?
No, no, absolutely. You see that this is not being minimized, right? This is your measurement error, or you know, like. Huh?
That is where my confusion.
Yeah. So basically, this set of measurement can be just a single measurement also, right? And suppose like either Gaussian, or suppose you're drawing it from Poissonian, and you get a count, some count X in one bin, right? And within the regime of within the fact that it's Poissonian, you can say it's X plus minus square root of X, right? But that is so they, because of the fact that you have taken it to be Poissonian. So you have a certain number of counts, and this is something you can state, right? Or you see that this one measurement has no difference between, like, there's no difference between this one single measurement and this n measurements, because here also you are actually calculating some you know some x bar, some mean, and you calculate some standard deviation, right? But you have taken this n points. Now the question you can ask is, if I repeat this set of endpoints one more time, do I get the same mean? You're not going to get the same mean, right? Like, so basically you will get x1, x2, and so on. Every one will have the same mean. So I have repeated it, like, let me just, in this case, since we have this discussion, let me just change it to m. So m data set points, each containing n sets of data, and you have repeated it m times, right? And you have like all sets of different m's. Now you actually construct a mean, you know, which is actually sum over like mean over all your m data sets, which are sum over, you know, an average over all of them, and you calculate the variance of that, and that is what that variation of the mean is what is going to do as well. Huh? That is a set of. That's a set of data. Yeah. Yeah. And then I'm doing another average of the mean. So your capital delta. So this is just gives me a mean. There's no way I can do an average of the mean, right? Yeah, here. And then I can do an average in this direction. That gives me a standard deviation. So I get mean and standard deviation. I repeat this process. I get standard deviation of the mean, and I also get another data standard deviation. Like you mean sample standard deviation? Yeah. I mean, but this statement is about the standard deviation of the mean. Right. Now my question is, now so why do I not take a whole data set and just get one standard deviation? One standard deviation. Yeah, of course. In that case also, like, right, so if you do the whole data set and calculate one standard deviation, that's a sample standard deviation, right? So yeah, so we are, it's nice. Let me just point this, since we are getting into this already. So we have, so you see that, like, suppose this one, in the first case, we calculate an x bar, which is actually summation, you know, 1 over n. I should just keep them separate now. This is, I'm calling it m. Otherwise, like, So summation xi I equals 1 to n. This is from one data set. And similarly, I calculate a sigma x bar, sigma square x bar, right? Which is like 1 over n summation xi minus this x bar. Right? So this is for my one particular sample set. My concern is that, and this is basically given, once I have a model from there, I can actually calculate what these things will be. We'll do that in the process. The statement I'm making here, so this would be my estimate for this theta, right? The question I'm asking is not the sample standard deviation or the data variance, but I'm really asking the question that this estimate, how much that is changing. So for that, I'm splitting it up, right? But for example, so how I'm doing that, so if you see that now, once I have all this, right? So I can actually calculate now the, so this is for n of them, right? So then I actually do this summation. I can put a I here for this thing. So I can do this theta estimate I, and that will give me a theta total, right? This is 1 over m. I equals 1 to m. I have repeated these data sets m times. And the variation of this, so sigma theta total square, that I can calculate this way, but that is actually connected to this sigma square by square root of n, right? And if I take, no, this is square root of n, right? This is the sigma square inherent. In fact, if you wait a little bit longer, I'll derive this more rigorously, but this is sigma square n, and if you would have taken the whole data set, then you would have seen this going as 1 over square root of n. In fact, I'll just do an example, one example to work. Just he was.
It's a very big question. So in the absence of the model for individual, can you just imagine this then theta as
yeah, so this is another very important question that you see that in the absence of a model for individual measurements, but if I really like these are really questions of when I'm trying to estimate a parameter. This is where it's coming in. But normally for individual measurements, if I do not have a model, all I'll say is that there's a mean and there's a standard deviation of the sample, like of the data sets. But this is really coming from the fact that I have a model and I'm trying to estimate the model. Does that answer your question? Or?
Sort of in the sense that I need a prefactor in front of scaling. That prefactor, even in the sort of model free case, I'm not estimating a parameter. Then the only other thing that's left of your measuring device.
Yeah, so that would be like, so this is what we are talking about here, that if you have a model, for example, if it's a Poissonian Gaussian, that would set that. Otherwise, it's the list count of your measuring device. Yeah.
Any chance to keep the generality of your treatment? Are you talking about the individual measurements are more like the chi-square, and then eventually you will be doing n times, and then you will be seeing how the is that?
I would not use chi-square here because that's slightly different. That's about the more of a hypothesis testing, like goodness of fit and so on. So this is I don't know what is the question that this
question is that if you are saying that you want to keep the individual S1, M1, D1 sets separate up to n times of that, and I understand this is a very general way of presenting beautifully the entire thing, but this model will probably be very powerful if you say that each individual measurements are also having an statistical error, whether least square or
no, of course, like maybe that is something I have not conveyed, that here behind all this goes the fact that these are all statistical systems, these are all stochastic systems. In fact, I mentioned it a little bit. I was going to develop this, that what do we mean by a state? That itself is basically like this, your system itself is characterized by a probability distribution, right? So like, once I start doing examples, I think it will become clearer. Yeah, any other question?
small delta theta.
This one?
The small delta theta, the smaller one.
This one, yeah.
This can be different for each and every measurement. Each and every measurement.
Well, as long as you're measuring in the same system, right? And as long as your measurement device, as Prasanna was saying, that it might be like coming from your inherent measurement noise, or it might be coming from the fact that you're actually trying to estimate a theta which belongs to a model, and you're trying to estimate a parameter of the model. So yeah, so that is why you're repeating n times, and that's the question you're asking by repetition, whether actually it helps in my measurement. And so like you cannot really have different measurements. That would account to like different systems altogether. And just to state, actually, like, you know, statistics developed in such interesting ways that the fact that repeating actually improves the improves your error in your measurement. This was not obvious even to probably the greatest mind in physics and maths we ever had, this Euler. Euler really argued with his mathematicians of his time that, you know, you should not be taking too many data, because, you know, your bad data kind of corrupts your good ones. So he said basically there is no reason to believe that if you take too many data, you actually do better. You know, so this is like trivial these days for us, but it has not been trivial for ages earlier. Yeah. Any other question? Yeah, so if not, let me just quickly, like I have stated, I think, remember that whatever discussion we had, once we start doing it with examples, I'll exactly come back to this point again. So it will become clearer. But the main showcase result is really the fact that by repeating measurements, whether classical or quantum, you actually can do better. And there are several, you know, motivations. Maybe I'll not write any of this since I might be running short of time. So there are interests presently, like particularly in cold atoms. There are interest in several scenarios. Firstly, as I was saying, that once you start having data which are few in numbers, like, you know, you really do not have a large quantity of data. And for example, we at some point did measurements where we are looking at like 3 photon coincidence, and after waiting 24 hours, you get one value, you know, 1 3 photon coincidence event. What do you make sense of the data? So if you have a like finite size data, that's where it's becoming very important. It is becoming very important, for example, in finding new physics which are very small. For example, LIGO is one example where these classical measurements have been pushed absolutely to its limit to find new physics, or there are this search for this weakly interacting like massive particles, dark matter, and so on, where also these are kind of the better you do in terms of estimating, the higher the chances that you will be able to see new physics. And besides the fact that you know, this everything that I till now motivated this quantities that I was talking about, that you're trying to estimate a parameter and how well it can do, this forms part of the precision measurements. And just kind of to showcase, this is the last part of the motivation that I'll talk about, that you know, for example, just this field, certain things they have like, you know, like for example, the like again like showcase results of the community. So time precision, how well you can measure time. So presently, I think the record is that you actually can measure a unit of time. So basically measuring frequency at the level of 10 to the power minus 18 seconds. This is also like 3 years. I think they have improved it further to minus 19. And similarly, this Landis G factor, this Sourav was talking about, this is another mind-blowing measurement, which is basically, you see that this is a constant of a theory, the theory that Sourav talked about, and you basically set up your system to get sets of data and measure your parameter. And this quantity, which is something very close to 2, is actually measured. You know, I'm just putting these numbers just to show that. So this is, you can actually look at this paper. So this is all these decimal places are actually real 2D force in experiments, and in many cases, so what this means, 76, this is one way of writing in atomic physics, means that after all these results, this last two digits 85, the error is basically plus minus 76, 85 plus minus 76. And these are, like for each of these precision results, like if you take pairs of these digits, these are like one PhD student's lifetime, like 6 years to get the result. And most strikingly, it's another PhD student's lifetime to put the error bars, another 5-6 years. So this is, you can actually see more details of this kind of measurements at John Doyle at Harvard and several other people. And this is probably the most accurate measurement ever done by humans because of the fact that simultaneously QED calculations, people have gone to like few more places, and each of these digits measurements actually match with those QED calculations. So nothing else we have that kind of precision. So with that, let me start now more general. I have more space. A little bit more, adding a little bit more realistic model to this, to what we have here. So let me just put this. So classical measurements, like if you see, like there are two kind of important things I stated here, which I promise I'll expand more. One is that the system state, what is the most optimal system state? So actually, if you have a system, for classical states, we really do not have like, what I really mean by the classical states are actually that there's a system variable X, and as a result, there's a distribution, a probability distribution of corresponding to this variable. And this is what I mean by system state of the system, right? And so I'll be talking of two examples over and over again. One is a coin tossing simple, that you are basically tossing coins and looking at heads and tails, and a very similar structure of that. So there you are, as you're looking heads and tails, you're getting 0 and 1s, and a very similar structure of that in the quantum case of like single photons coming and you're saying clicks. So in that case, basically you have just this usually is just a probability of discrete variables x1, x2, and so on. And this is often called the probability or point mass function. And this is all about the states. So this is for discrete variables. But you might also have, for example, the same state is actually specified, might be specified for a set of continuous variables, and this, usually is represented by Px dx. So this is a probability density function, which is for continuous variables. And this is the system, and the examples of this, as I was saying, that I'll take. You see that the moment I'm actually stating a probability, there's some sort of a model underlying, right? For example, if I'm actually tossing coins, I have some sort of a binomial distribution in mind. So there is a particular model corresponding to this state. If I am actually like sampling from a continuous distribution, so then basically, like for example, there might be a model where X is actually Gaussian, and I'm actually sampling from the Gaussian. And in that case, the parameters of the Gaussian are the parameters that I'm trying to estimate. And either way, this once you state the probabilities, you basically state the system. And since we are talking of probabilities, let me just state here, again, this is something, a very important part of this kind of parameter estimations, and since probabilities play such an important role, everything is stochastic, that even in agreeing on what is the nature of the probability, there seems to be a big disagreement, or not disagreement, but there's a big kind of two different schools of thought in even agreeing the fact that what would be probabilities. And this is something kind of a topic that not only makes this field very interesting, but also kind of a little philosophical, in the sense that, you know, what do we really mean by information, or what do we mean by measurement? So let me just state this, and again, like these two different schools of thought, I'll come back over and over again. So it turns out that normally when we talk about probabilities, so we have this kind of ideas that, you know, these probabilities that we are talking of are actually some events that I'm interested in over the total number of events, right? And in the limit, this probability is basically the limit that this n tends to infinity. Right, so it is the frequentist approach, the frequency of occurrence of that particular event over the total number of events in the limit n tends to infinity. So this is what we are usually used to. But then there's this other school of thought. This like Bayesian probabilities are like people who comes from the Bayes school, and they would say that this is kind of, you know, like not very sensible thing to do if you are a real practical physicist, because how many times you really can take n tends to infinity? Like, you know, like this is kind of meaningless. In fact, this whole Bayesian school started from this amazing paper by Bayes, who kind of set up this whole thing, saying that, you know, like, he was basically pointing out that people who look at this frequentist approach, they're kind of believers of something. They believe that these probabilities exist, independent of whether I'm looking at it, or and so on. But actually, this is like finding this probabilities n tends to infinity is not the most important question. He was asking, and if you see like the question he was asking is again so important today. He was saying that, you know, like the most important question of probability, particularly when you are actually using it for experiments and for processes, is that are questions like this, that I am tossing a coin and I toss it 7 times. Right, so so toss a coin, and you out of 7 times you basically get 4 heads and 3 tails. Can I predict what would be the result in the 8th draw? So he's basically saying that, you know, like you see that like you are given a coin, you don't know the bias of the coin. So basically a coin is a 2-state system. So a coin is just given by P of the probability of head. If you know that, you know everything about the system, right? So, and the frequentist would go ahead and try to imagine this P as a ratio of kind of this frequency of occurrence. So, you know, and n tends to infinity. But Bayes is pointing out, and which is today really the point that we face every day in the lab, is that rarely or never ever you are actually taking things to infinity. So the meaning of probability is basically the following, that when you have a coin, initially you know nothing about P. Right, but it's a random guess. You can actually guess that, you know, the coin is probably fair, given to you that head and tails are 50-50, but you really do not have any information. But as you start throwing the coin, you know, the first time you get head, second time you get head, and suppose you have 2 heads after 2 consecutive throws, these 2 heads actually immediately tell you something about what to expect in the third row and fourth row and so on. So he was basically pointing out that the most important question is, you have a finite number of stochastic events. You have taken a finite set of data. Can you predict what will be the next set of data, for a finite situation? And that's really the question. And as a result, the Bayesian, in fact, I'll come to it more in terms of how they look at whole estimation and the way they vary. But for the Bayesian, like this is the first introduction to this point that will come back over and over again. For the Bayesians, there are several point of differences between the Bayesian and the frequentist. But for one thing, that they not only do not agree that probabilities are fundamental, but they also do not agree the fact that I am trying to measure this system X, and suppose in this system X there's a parameter theta, right? So basically these probabilities are functions of theta, and that theta is what I'm trying to estimate, right? Like, so I can actually try to estimate that. So the way we look at it, for example, this number I quoted, this Landis G factor, almost all physicists you ask will say that, well, this G is kind of a God-given number, it's there and it's our task to find it. But the Bayesian approach is that really all these things are actually, like, when you're actually trying to estimate theta, you're never really trying to find a parameter theta, but you're actually trying to find the probability or the distribution of theta. In fact, like, they would never, like the Bayesians would never actually agree that there is a fundamental theta naught, because even if there is a fundamental theta naught, we are never going to know that, because as far as our measurements are concerned, they are always stochastic. So it's meaningless kind of to talk about theta naught. Instead, you actually talk about p theta, the distribution. You start with some distribution, and like theta is a stochastic variable, and then you do measurement, and you actually update your information, like how much information you had. So for example, like you are taking this data, so you have p theta to start with. Some you might not have any information about initially theta. So for example, if theta is really an angle, you can actually take it to be equally distributed among 2 pi's. And now you take a set of data, and you want to know what is theta given that you have this data set. So let me put it this way. This data set basically means x1, x2, xn. You have taken a set of data, and you are asking how this has gotten updated. And this is where this Bayes theorem comes in, that it actually tells you that whatever p theta you had, you started with some p theta, that is your knowledge, initial knowledge about the parameter, and after your measurement, you're basically updating, and this is the Bayes rule. If you see, like, this is just p a given b is p b given a, and so on. So it's basically an update of your priors always. Like, it's always, you start with your total ignorance, which is characterized by p theta, completely flat, and then you keep updating your thing. So this is the state of the states of classical systems. And given that, any questions up to this point? If not, we'll again come back hopefully to this few more times to this, like, same results, but how Bayesian and the frequentists will interpret differently. And not only that, for at least a couple of cases we'll do, where you will see that the Bayesians and the frequentists, it's not just philosophical of how the probabilities are interpreted, but actually they get different answers based on, completely different answers based on which way you're actually, whether you think of these parameters are actually just updating, or whether you are actually trying to estimate theta naught through the frequentist. Yeah, any questions? Huh? Yeah, so that's an interesting question, particularly because if you do not have anything to start with, if you're completely doing this unknown parameters. So So one good thing is that in many cases, particularly if you take this n tending to infinity, the Bayesian and the frequentist actually agree. But there are cases which you can design where actually you will find that so you can basically do things like, for example, what the frequentist will give you an answer in a particular scenario, what the Bayesians will give you an answer in a particular scenario, and what common sense will give you an answer. And then you compare. So let me give an example that suppose this kind of things that Sourav was talking about, that as a function of time, you know, so you have an atom kind of staying in the excited state and then decays out. This kind of a curve, suppose like there's a theory and which tells you so some sort of a decay even, and then there's a time at t naught after which it decays, right? And you know, and you are basically you're using data, you're collecting, this is your underlying theory, and you start collecting data to estimate t naught, right? So you start basically binning. So suppose you get this like three, like you have 3 points where you're binning. So let me put some numbers. So let's say this is like some 10 seconds or something, and this is you're binning at 12, 14, and 16. So this is a case where actually you can compare these things. So for example, you can actually do a frequentist way of analysis, which is what we'll actually do. Mostly will develop this maximum likelihood method. So there is a method which is basically we have already written here. The kind of, if you do it this way, you kind of calculate averages and so on. So you can actually do it through that frequentist way of analyzing, and you find that you know, this t naught, the estimate that you get is something like you know, 12.3 or something like that. Right, in this particular case, like somewhere here, which is, you see that it is clearly like breaks your common sense, because if the atom or the nucleus is decaying at this point, then these are the three data sets you have gotten. So at least the t naught estimate should be smaller than the smallest, right? So at least t naught will have to lie somewhere here. If you do the Bayesian estimate of the same problem, just mechanically you do the Bayesian estimate, you get something like it lies between like 8 and 9.5 or something like that. And if you do the common sense experiment, yeah, you will say that it is less than 12, right? Whereas Bayesian is actually like a frequentist actually gives you larger. And this particular example is due to Jaynes. You know, there's the same Jaynes of Jaynes-Cummings Hamiltonian, and I'll actually give a set of references for all these things. So out of which Jaynes's this papers on the statistical analysis are quite amazing. And this is one example he actually cooked up, but there are several such examples which are artificially constructed, but very important real life examples to see that the frequentists and the Bayesians can widely differ. Actually, they can very like even like, you know, the frequentists can go wrong at the level of just common sense. Yeah. So I think I'm really short of time. I think I'll skip. I had a little bit more of the noise, like adding noise and so on. But let me just kind of. Or maybe anyway, since we are just doing this part, let me just state this. Yeah, so actually, if you see, this is a state that I was talking about, that there is a system whose state is x, and px is the state, and the variable we are measuring is x. And this actually, this is our measurement, which gives us another variable y. And usually this is, there is another bit of complexity which by itself is very interesting for us experimentalists, and that is the fact that there's a noise that actually also fits in. So if you see there's a, what we see y is actually, not directly x. In fact, x is our system and we want to really infer about the x variables by measurement of y. But in the process, this noise gets added. So y, if you see, it is some function of basically x and noise. Right? And so you are never really directly seeing the variable, you're seeing always in presence of a noise. And then the question is, how well you can do so. In fact, I had a little bit of more details on this, but let me get to an example because I think doing it through examples will be far better. So let me take a very simple example that just consider the fact that, you have a variable x, which is just a binary variable, so it can take 0 or 1, and there is also a noise variable, which actually just takes two values, 0 and 1. And this too, so this is your actual system that you would like to look at, but this noise gets combined with it, and there is always some underlying form in which they get combined. So let me take this one particular form, which is basically y is given by so this is a XOR gate. So this example is basically what people will call a bit flip error. As in, this particular example? Yeah, that's exactly what I'm calculating. That's exactly what I'm calculating. So you see that I can actually construct a truth table to see how my original this thing gets messed up. So you see that for x, zeta, and y, so if x is 0, zeta is 0, y is 0. That's the nature of XOR. If x is 1, zeta is 0, y is 1. If x is 0, zeta is 1, y is 1. And if this is 1, this is 1, this becomes 0. Right? So it actually flips the bit. You see that this part is a very accurate representation of the input source, but this is actually here you see that there's an error which is actually flipping the thing. So you can actually start calculating what Professor Dattagupta was asking, that you can now start calculating the errors and so on, and you see that so you can actually so if we say that, so the probability, we are assuming further that the probability of the noise taking the value 0 is mu. So the probability of noise taking the value 1 is 1 minus mu. So then we can actually start calculating just from this information. We can start calculating the averages of y, which is basically just ypy. You can either use the truth table or this probability. So you see that this is basically, let me just write the result, and I can put this as a homework. It's really like 2 lines to see this, that this is basically so if your signal basically is this average of x, you see that the average of y is through this addition, is actually not only getting scaled. If your average x is not only getting scaled by 2 mu minus 1, but it also has a shift, right? So it changes, and you can actually calculate the variance in y, which is And you see that basically that again you see that there is a shift, and the variance of x is actually getting scaled, and you can see that there are two special points, which are mu equals 1 and mu equals 0, for which the shift, so for mu equal, so you see that for mu equals 0 or 1, variance of y is equal to variance of x, which is basically saying that if the probability of the noise taking that value 0 is 0 or 1, which is actually saying that either the noise is not there or the noise is all of it. In both cases, somehow your the variance of x exactly remains the variance of y, and you will see that these two cases, these two kind of probabilities, these extreme points are special cases. But other than that, everywhere, all other points you see, in fact, you see that the variance of y is actually getting contaminated by the variance of x, or the variance of the noise. And in this kind of a scenario, you see that we actually used a model corresponding to the state of the noise to derive this. But usually, if you do not have a model of noise, how do you go ahead in calculating the variance? That these are some of the very important questions we'll be encountering. And in fact, you can, as I was saying, that you have this continuous wave and or the continuous variables and discrete variables. So similarly, you can take this another model for by taking this as a continuous variable. For example, you can choose the noise, so if x is a probability density, like px is a probability density function, so you can actually choose the form of the noise as, suppose p zeta. So this is the continuous case now, continuous variable case. So p zeta is being drawn from now, let's say a Gaussian. And you have an update rule. You're given a case where y is, yeah, mu equals half. You see that firstly, the variance completely goes away. In fact, you can actually plot this as a function of mu. So you start, you're plotting variance of y as and you see that it has actually a behavior like that. So it kind of goes to a constant starting from variance of x. Right? So, so this becomes basically 1/4, I think. Yeah, so it is equally, like, in fact, mu equals half is the worst possible case, right? Like, just like mu equals 0 or mu equals 1, either you do not have the noise at all or you have all of it. In some ways, that is equal to knowing your signal, because it's either the opposite. Mu equals half is the worst possible case, where basically, the noise is precisely contaminating and you do not have any information whatsoever. In fact, your variance of x completely drops out, basically. So you have no information whatsoever about what your signal is. Yeah, so that's kind of the, the maximum mixing. And here, if you do the same thing, you see that if x is a Gaussian random variable, these are all like continuous cases, and zeta is also of this form. So x, basically by Gaussian random variable, I mean that x is also being drawn from a distribution. So px is some Gaussian. So so here you can firstly, anyone, like, if this is a Gaussian, this is a Gaussian, when you add them, what would be the distribution of y? It's also a Gaussian. Yeah. So you can actually, so you can basically write down the distribution of y and calculate again. It's you know, like your the mean and the variance corresponding to this. So you can actually calculate the variance of y, and what you find is that the variance of y is basically it's basically sigma square plus delta square. Whereas you know, the average of y remains unchanged. So you basically you know, like see that noise kind of shifts the variance and actually makes the variance worse. The same kind of in both cases. And then the question then becomes, and here if you see, I was just taking artificial cases of actually models of noise either in the binary form or in CW in a continuous variable. But in most cases, you would not even know what is really the model of the noise. So in that case, in such cases, how do you actually separate out the signal from the noise, or how do you actually make a model of the noise? And that's, I think, where we'll head out to, which is basically saying that if we do not know anything about the noise, except that I think all this discussion a little scattered, but is kind of conveying the fact that your system is stochastic, your measurements are giving you a set of data in which noise is also getting added. What would we do with the data? How would we actually combine and mix the data to find an estimate of this parameter, you know, given the fact that noise is adding and we do not have a model of noise, right? So I think this is kind of, I can see that it's almost a class time, and it's kind of like setting up the stage for what I was planning to do. So any questions up to this point? Yeah. So it really depends from case by case basis. So it turns out that if you have a large sample size, mostly the Bayesian and the frequentist, they agree. And I'll basically, the main point of this, all sorts of these lectures are how to handle the data and how to like process the data to get these estimates. And there, as we do this maximum likelihood and so on, you will see that those methods have a Bayesian interpretation and frequentist interpretation because of the fact that we are taking very large sample size. Where this really start differing are cases, I think I erased some of those, but are cases where you actually start having a small number of sample size. They start differing widely, and you can have like very strikingly different results. But those are all case by case basis. It's not that always frequentists and Bayesians are doing it. Many of the times it's actually just interpretations. Yeah. Huh? LPT? Oh, Hongu-Mandel. Yeah. So that's kind of goes back here. That are you talking of like Hongu-Mandel, like just? Yeah. So when you are talking of Hongu-Mandel, it's slightly different because that is a question more of like, if I understand the question correctly, it is more of a question of hypothesis testing. That so. Yeah, so that's why I'm saying that it is a. I'll come to the coincidence counts reduction, but so in Hongu-Mandel, actually, basically, you have a scenario where you have a photon, like hopefully derived from the same coherent source, but 2 photons are coming on the detector, and these are like just single particles on a beam splitter, and then they split up. And if they are like perfectly timed and all that, then I'm actually like the Hongu-Mandel is saying that if I have 2 detectors here, and if I ask whether there is coincidence, and like whether so basically in the Hongu-Mandel case, actually because of this interference, what we find is that either the 2 photons go one way or the 2 photons go other way, but we'll never find 1 photon go this way and the other photon will, right? Like so basically this one probabilities are, they just come with opposite signs. So there you see that if I actually start looking at the signal, so this is coincidence, as a function of some delay, I'll basically find that when the delay is exactly like 0, if the 2 photon wave packets are kind of nicely matched, then I'll actually see that this coincidence kind of dips down, right? And you see that this is why I was saying that this is more like a hypothesis testing, because if I manage to have 2 single photons, I would use this as a test, the fact that I am actually sending in 2 single photons and they're interfering, to have 2 like one photon probabilities canceling out the amplitudes. So as long as I see this signal, like as long as this coincidence, basically if it's normalized, as long as it's dipping, I'll say that I'm starting to see the Hongu-Mandel dip. But I'm not trying to estimate a parameter from here, right? No, I understand. I'm getting back to your question. Yeah. So I'm getting to your question. So you see that, like, firstly, I'm not estimating a parameter. I'm really doing a hypothesis testing, where actually my hypothesis testing is, again, technically, very technically, it's just yes or no, that whether actually I have see a dip at all or not. But then again, like in hypothesis testing, as we talked about earlier, that this question becomes important, that, you know, how much of the dip I see. And if you see like this coincidence that I have drawn, particularly in this Hongu-Mandel case, these are like just basically histograms, right, at different time bins, right? So again, like exactly the same thing, that how much I have. And this here, if you see, these are just histograms, as in these are just like N1, N2, and so on, the number of counts that I see. And these are, otherwise, since I'm doing a hypothesis testing, I'm not measuring a parameter. I would basically do this experiment by sending these pairs over and over again many times. And in that case, for each of these n counts, I have again a plus minus square root of n scaling. And this is something we'll do hopefully in the next lecture today. So basically, for each of these histograms, you will have a error bar which scales with the number of counts. So you see that, like, you know, if you have not a very good dip, and if your error bars are this big, so that is not a good, you know, good signal to noise to say with any confidence whether you actually have a 2 photon interference measurement. So you would then just do a straightforward thing of taking many counts and trying to bring this down. So you see, like, basically the point is that though Hongu-Mandel is an example of a quantum interference phenomena, and I'm really trying to test that, but this measurements and the way I'm actually establishing the hypothesis is a very classical process, in the sense that I'm basically just doing counting of what I see in the detectors is just counts, and I just do the counts. Law of large numbers, I see a square root of n fluctuation, and the more counts I gather, the better I can actually estimate. Yeah, any other question? Yeah, questions will be better. I think I was very scattered, so I just couldn't start also the max. So we can just discuss here.
Yeah. So I have, since this plot is there, suppose I have access 0 to 8. So I can only have one figure positive. I cannot have negative. So
Here?
I can have, I'm looking at some time and I will either have 1 count or 2 count or no. When I put the error bar, right? Is it fair to put an error bar which is on both sides of the mean?
I see. So, but square root of n is always smaller than n, right? There is no scenario where you are going to get anything small. So this is n, right? Like this is just the number. Huh? Square root of like 1 or 0. Like you are never going to have this smaller, right? Like so you have n plus root n, but n minus root n is also larger than 0. Is that answers your question? Right? I'm saying that here, suppose you're very close to this. So you have an error bar. Like if you have 1, you have square root of 1. So you have basically this error bar is telling you it goes from 2 to 0. Hmm? No, here it's just a number. Yeah, so you're, well, we are not calculating any average. We are not calculating any number. Like you see, the only thing we want to see in this kind of a measurement is coincidences at different times, right? So how would this experiment go? This is T1, T2, T3, and so on, right? And every time bin, we have a certain number of counts. It can be 1,000, 10,000, but it can be also be 1, right? And given the number of counts, and I have always, of course, like I might have waited for a long time, and this is what I've gotten. So then I put the thing that this is like just n plus minus square root, because it has been taken for many times. But of course, this n can be 1. Is that what you're asking? Yeah. Huh? No, yeah, it doesn't go to below 0. But of course, like, yeah, no, as n is smaller, the relative error bars are larger. Yeah. Yeah.
Hello. Hi. So if I match this Hungomandel experiment with that measurement scheme, here you just said.
Yeah.
So if you see here, the system, if system, there is a correlation between systems, then we expect that the error is 1, n.
Yeah, but you see, yeah,
but when you are doing that Hungomandel,
yeah, but Hungomandel is a scenario where we are not doing parameter estimation, right? We are not trying to minimize any error, except that this is a scenario exactly of the star detection that I was talking in the beginning, right? We are drawing a line. So here, in fact, exactly that, right? Like if this is my count, I have a very little thing. I would like to draw a line that where I would say that I actually have like something below 0 when I do have an interference. Where do I draw the line? And that is where this discussion was happening, square root of n. But I'm not estimating any parameter. Yeah. But like you can actually use this kind of a thing to create a Mach-Zehnder interferometer and estimate some theta. In that case, you are asking a parameter estimation. This is just kind of testing your hypothesis. Do photons do they interfere, or in the 1-1 is it really dropping? Yeah, I know. Yeah.
So suppose I'm talking about this part of your talk. So suppose I want to play the devil's advocate and say that, okay, I have a set of measurements, which is this first set of measurement, D1. So I have taken some 100 measurements, but I know that you're assuming that there is some distribution which is random, right? It is drawn from some random distribution, right?
Yeah, all are random, by the way, like everything.
Everything.
All
now,
these things are random.
So I just want to be lazy and I say, I don't want to repeat it again m times. I will just now ask a computer to pull out randomly 100 numbers from some 10 numbers from that and generate sets of data. Each of those sets, suppose there are sets of 10, will have a mean. And I can...
For those sets of 10, you will have a mean. Yeah.
And then I take the means of these means. So it is again going to...
means of means and the
standard deviation.
RMSE of the mean will be 1 over square root of 10 times.
So then the question is, do I need to do this set of m measurements, or I just do this 100 measurements and just try, if it is drawn from a random, I can argue that I'll just draw numbers at random.
Yeah, that's kind of what we are doing here. That's exactly the thing. Here we are we know the answer, so we are putting in n plus minus root n. But the point is that, as long as you agree that when you're putting that 1 over root n for one set, you are using a known result, but that set itself doesn't tell you anything, right? Because it's one number and one random variable, right? The mean of this data set is also a random variable because it's a mean of a set of random variables. So it's just one random variable, it says nothing. But if you know the answer, you can try to do that, except that you would not know what is your mean.
No, so no.
What is your like average mean?
No, so what I'm saying is, see, this 100 series will have a mean, right?
Yeah.
And you know, if you do what you are saying earlier also is that the mean will not sort of change. What you are trying to put is an error bar, which is the standard deviation of the means. So if I'm only interested.
So the mean, see, like the thing is that if I put the means here as like x1 bar, x2 bar, and so on, and if I plot the mean, you know, so x bar, if I plot this means that they are changing, right? So I'll actually again see a set of histogram.
I agree.
Right? And the width of that is what we are concerned about.
I agree. So what I could do is, I agree with that. So in that set of 100, I can say, I can take the first 10 data set and just write a mean for that. I could take, so from 1 to 10, I could take a mean, I could take from 2 to 4, another mean, and I can generate an arbitrarily histogram like that, which is like.
Yeah, absolutely.
There will be different, right? They will give you different numbers.
They'll give you different numbers, yeah.
So do I really need to do a repetition of the measurement, or I just have a sample and just draw partially from that in arbitrary random way?
No, but these partials are always like smaller sample sets. Now, out of 100, you're choosing like 20 or 30. Otherwise, if you're dealing with 100, it's always the 100.
Yeah, but I could do 50 out of there. I could do 10 and find them.
Yeah, but you're
randomly.
That is what here you can say that there are m times n number of data sets, which you're randomly partitioning. You're saying that I'll not bother about m. I'll take n and partition randomly, and I'll get some small n1 square root of n1 square root of n. Yeah, but you otherwise see, like, you're not gaining anything by doing this partitioning, except that whatever you're partitioning, you can only talk about the variance of that particular mean. That's the only thing that's coming. Yeah. Yeah. Okay. So variable data sets, you're saying the length of the data sets are different.
But in one data set, we got 10 data points, and in the next, maybe 30 on the 40.
Yeah, but the time being fixed is the same. The
time is fixed.
You see, like, I can think of x1, x2, xn in your example as the counts I have gotten in a time bin, a certain time bin, right? So you're saying that, like, in some cases, x1 might be 0.
No. Means for 10 hours, we'll get the data points only 10 times.
Only 10.
Yes. In another, for the another time zone, I just get maybe 5 times. So then what will be the effect of that different data points in a particular data set on the final results? Means on the variance or the average.
So that's what I'm trying to say, that you got different data points, but your binning is the same size.
The size should be the same.
No, that's what you said, no? 10 hours of binning.
Yeah.
And each binning you are getting, like, in some you are getting 10 points, in some other you are getting 5 points. So that's exactly this scenario we are talking of. So here, this n is the binning time, right? And x1, x2 can mostly be 0. Like, out of this, 5 can be non-zero, just 1, 1, 1, 1. You know, here 10 can be non-zero, and so on. So this n is just the binning time. These are, like, you know, within that binning time, like, you might not, like, x can be 0, 1, 2, 3, 4, and so on. Right? So this is exactly the scenario, basically. Just like, you know, just that I have written x1, x2, you don't necessarily need to take them non-zero. You can take them, they can be 0 as well. Yeah.
Hello. The variance of y and variance of x, it is equating, and I see that it is happening. Is it because the input and output, I have only 0 and 1 among these two?
Yeah, no, so basically, like, you see, this happens firstly, what this means. This basically means that whatever uncertainty you had with X, you have not added anything.
Yes.
Right? Your measurement uncertainty is exactly the same as your source uncertainty. Now, when are this coming, like happening when mu, the probability of getting one realization of the noise is either zero, which is basically means that, you do not have a noise, or it's one, which is basically saying that it's completely noisy. So either cases, you see like 0 and 1 are two extremes. Right, they're like either you know nothing about, either the noise is not there, or the noise is completely determined. Like the noise is actually what is setting the thing. In these two cases are both deterministic cases, and in that cases you are not adding any further variations.
I'm saying that if it is 0 and 1, the input and the output is 0 and 1 among these two probable values only, this thing is only possible then because that average of x that comes in the average of y equals to 1 minus 2 mu minus 1 that comes there because that average of x is equal to p x equal to 1.
Px,
equal
exactly.
to 1. That
but you are just expressing it in terms of like you are just using that y is x plus zeta to actually find that. Yeah, but what is the point you're saying?
I'm saying that if they are like series of values, other values like 0, 1, 2. Many.
Yeah, of course. Then it's a different. This is just for binary. It kind of works. Like this kind of a result just works out for binary.
And the graph.
And you see, like otherwise, like that mu equals 0 or 1 will not have much of a sense if you have many such values, right?
Also, that graph.
This graph.
Yes. That so mu equals to 0 also coincides, right? Variation of y equals to variation of x.
Yeah, I think so. Yeah.
So
this is mu equals 0 and 1.
Okay. So no, I'm saying that variation of y and variation of x, they are like.
Yeah. So sorry. This is very rough. My writing just got worse and worse. So variance of y. This point is variance of x. They coincide.
Are they coinciding there when mu equals to 0? I mean, it's
mu equals 0 and 1. No, they coincide.
1, I can see that they are touching each other.
So 0, they are not coinciding? No, they are, no? Mu equals 0.
No, I mean, calculation wise, it is okay. I can see, but.
Oh, then make them touch. Yeah, I don't know. Yeah, they are basically the same. Yeah. And this is, I drew this also because I don't know if any one of you know entropy and Shannon's entropy for which I was planning to talk today most like this class, but in fact I completely ran out of time. But basically, like, if you calculate an entropy of a heads and so on, you will basically find the same curve, and it has the same meaning for mu, for p equals 0.
Okay.
Huh?
Hello.
Here, actually, we have not come to time and spatial averaging yet. We are just talking of ensemble averaging. So that way the ergodicity is not coming into play. But if we had systems where actually, like for example, if there's a Brownian walk, or if there's a quantum jump of a 2-level atom or something like that, in that case, or a collection in space, in that case, the questions of ergodicity will come in. Here, these are now presently all stochastic averages.
Yes. So by doing measurements, can you test whether your system is ergodic or not?
Yeah, that yeah. So in that case, basically,
By noise analysis.
Yeah, the ergodicity tests are usually like very complex, in fact. Yeah, but somehow, yeah. So yeah, like you would like to, yeah. The only thing I can imagine is like something like Brownian walking, or like there's a kind of a like maybe an atomic gas diffusing and so on. And if you actually have a measurement where you collect the light from the entire gas and kind of focus it down on a detector, versus if you actually have kind of a Heisenberg microscope where you look at one particular point T and try to see if these two averages give you the same. I don't know whether this will also work, but yeah. The ergodicity averages measurements are usually very, very difficult. Mostly like we assume that it's ergodic, and so, and luckily in quantum optics, we do not have much of like turbulent systems and so on, but I don't know. Yeah, I don't know. Yeah, how would a measurement look like? Huh?
Hello.
Any other question? Oh, yeah. Where should I look?
Hello, sir, I have a question.
Yeah.
Okay, so what is the actual physical origin of this bit flip errors you mentioned about, like how bit flip errors are the origin of?
Yeah. So what is the question?
What is the origin of this bit flip errors?
Okay. So so what is the origin of noise? That is probably the question. So that can be like, like they're here presently, you see that the noise is just taken a particular form. So, this, it's kind of strange, like this is the first time I'm doing this hybrid. I don't know which direction to look at, because it is online. Yeah, so this noise zeta that was being added. So this is basically just flips the bit essentially. And this can be for various different reasons. Like you might be trying to transmit the signals through a fiber channel, and this might be just thermal noise that's actually coming in and so on. So yeah, so noise is, in fact, this is another whole direction of what are the sources of this noises and errors, and there can be many different kinds. There can be short noise, thermal noise, and so on. Something that basically adds to the signal and changes it. Does that answer your question?
Because I have a question, like, so in optical cloaks and other some optimization problems, like we use alkaline earth metal like elements instead of alkali elements, which have a more complex level structure. So like I read somewhere that it using alkali elements will reduce these bit flip errors, and like I don't know how.
Oh, that I don't know under what circumstances, but for example, you can imagine a scenario like this, that you have a cavity with a two-level atom, and this is your X, which is a single photon going in, and you have a detector here, and now along with that, there's another photon that comes in, which is basically just a random noise photon, and both are coupled to the cavity, and you're basically seeing it on the detector. So you see that if this guy comes in, will pass through. If this guy just alone comes in, will pass through. But if both of them together comes in, there's a photon blockade, provided you have designed the cavity to be a strong coupling cavity QED regime. So both of them, there will be a photon blockade, and this exactly will realize kind of a bit flip error. And from that perspective, I don't know, like to get to cavity QED, you might actually require like these atoms with very strong dipole moments and so on. So, otherwise, I don't know why bit flip errors, which are very technically just digital errors, should come into.
Okay, that's why I asked about the origin of this error. Okay.
Any other question? No? Fine. Yeah. Okay.
So please put your posters up.
Yeah, please put your posters up. I basically just covered 4 pages.
Yes, sir. Usually.
So poster